Poster number 1 presented by Professor Osama Osman titled Computational Notes on the Graphene Quantum Dots Substituted by Phosphorus, Arsenic, and Antimony Atoms. Graphene quantum dots are nanoscale structures of graphene having strong quantum properties and edge effects that result in unique properties. As shown in Figure 1, a graphene quantum dot in the shape of an armchair hexagonal C42 is subjected to substitution by phosphorus, arsenic, and antimony atoms. Density function theory calculations were used to investigate the influence of filling with 4 phosphorus, arsenic, and antimony atoms on armchair hexagonal C42. At the B3LYP 6 to 31 grams d.P. level, the effect of substitution on electronic characteristics was investigated using density functional theory. Some descriptors were calculated for model molecules to study the effect of substitution. Each structure is optimized, then some parameters are calculated, including total dipole moment, the high occupied molecular orbital and the lowest unoccupied molecular orbital bandgap energy, and the molecular electrostatic potential. The reactivity of the studied surfaces is indicated in terms of the calculated molecular electrostatic potential, MESP. After collecting the studied parameters together, a computational note will dedicate the studied GQDs for appropriate applications.
This poster undertitled The Electronic Properties of Graphene Quantum Dots Substituted with Aluminum, Gallium, and Indium Atoms. The major aim of this study is to develop the electronic properties of armature hexagonal C42 graphene quantum dots by decoration with aluminum, gallium, and indium atoms. All calculations are carried out utilizing Gaussian 09 packages at Spectroscopy Department National Research Center. Building model molecules, the supposed structures of graphene quantum dots consisting of 42 atoms of carbon with armature zigzag edges. The electronic properties of armature hexagonal graphene quantum dots were tuned by substitution with the aluminum, gallium, and indium atoms in 4 different positions. The results indicated that the electronic properties of graphene quantum dots in the armature hexagonal shape substituted with aluminum, gallium, indium atoms or in the 4 different positions were investigated successfully using density functional theory. The electronic properties of the studied structures were calculated using the P3-Lib method. The replacement of carbon atoms with aluminum, gallium, and indium atoms increases the total dipole moment of armature hexagonal C42 while decreasing the HOMO-LUMO band gap energy. The replacement with 2 aluminum atoms is the most effective model as the band gap decreased from 3.4 to 0.2 electron volt. The molecular electrostatic potential maps revealed that the reactivity of armature hexagonal C42 was increased by substitution with 1, 3, and 4 atoms of aluminum and with 1, 2, and 4 gallium atoms. Meanwhile, the substitution of armature hexagonal C42 with indium atoms doesn't affect the reactivity. As a result, replacing carbon atoms with aluminum and gallium enhanced the surface reactivity of armature hexagonal graphene quantum dots.
Poster number 4 presented by Professor Abdul Aziz Mahmood titled Density Function Theory Calculations for Graphene Quantum Dots Filled with Aluminum, Gallium, and Indium. Density function theory calculations were used to investigate the influence of filling with 4 aluminum, gallium, and indium atoms on graphene quantum dots in the armchair triangle cut. Some descriptors were calculated for model molecules to study the effect of substitution. Such descriptors, including the total dipole moment, the high occupied molecular orbital and the lowest unoccupied molecular orbital bandgap energy, and the molecular electrostatic potential, were computed. To investigate the electronic properties, B3LYP 6 to 31 grams d.P. level for aluminum and gallium and B3LYP 3 to 21 grams level for indium were used. According to the calculations, the band gap result indicated that the armchair triangle graphene quantum dot band gap decreased with the filling of aluminum and gallium, especially with the filling of 2 atoms. Also, in the instance of indium, filling with 4 atoms was the most effective on the armchair triangle graphene quantum dot band gap. Furthermore, the molecular electrostatic potential map results showed that the armchair triangle graphene quantum dot map was not affected by filling with 2 and 4 atoms of aluminum, gallium, and indium. Finally, all result indicated that in the case of 1 and 3 aluminum, gallium, and indium substitutions, the surface of the armchair triangle graphene quantum dot layer enhanced sensitivity and surface area. Number 5, titled Effect of Hydration on the Physical Properties of Graphene Quantum, presented by Medhad A. Ibrahim, Spectroscopy Department, National Research Center, Giza, Egypt. Graphene quantum dots having strong quantum property and edge effects resulting in exceptional physical, as well as chemical properties. Accordingly, 4 types of graphene quantum dots, namely armchair triangle C60, armchair hexagonal C42, zigzag hexagonal C54, and zigzag chair triangle C46, were subjected to quantum mechanical calculations at DFT V3LYP 6 to 31 grams dP. Each model is subjected to hydration up to 6 water molecules. Total energy, total dipole moment, and the high occupied molecular orbital and lowest unoccupied molecular orbital bandgap energy were calculated. Results indicated that the total dipole moment of armchair triangle is increased because of increasing the water molecules, while increasing water molecules slightly decreases the bandgap energy. The same is regarded for other types of GQDs. Another important effect for hydration is to map the molecular electrostatic potential MESP for the studied models to indicate the active sites upon the surface of GQDs. Results indicated that water as polar molecules redistribute potential all around the surface of GQDs.
This poster undertitled on the substitution of aluminum, gallium, and indium with the graphene quantum dots. The main objective of this study is tuning the electronic properties of graphene quantum dots by decretion with aluminum, gallium, and indium atoms to enhance its surface reactivity. Calculation details: model molecules representing graphene quantum dots, Z hex C54 and Z hex substituted with aluminum and gallium, are subjected to optimization utilizing density functional theory at P3 lab 6 minus 31 GDB basis set, while all calculations for the indium atoms are running at P3 lab 3 minus 21 G star level of theory. The conclusion: density functional theory have been used to study the electronic properties of the proposed structure of zigzag hexagonal graphene quantum dots consisting of 45 carbon atoms and graphene quantum dots substituted with aluminum, gallium, and indium atoms. The substitution of Z hex graphene quantum dots with aluminum, gallium, and indium atoms significantly increases the total dipole moment, especially in the case of substitution with gallium. The increase in the total dipole moment values reflects the high reactivity of the studied structures. Additionally, increasing the number of aluminum and gallium atoms results in an increase in the total dipole moment values. However, the total dipole moment values increases with increasing the indium atoms to 3 dpi. Additionally, the substitution of carbon atoms with aluminum, gallium, and indium results in a decrease in the band gap energy of Z hex C45 carbon atoms. Increasing the number of substitution atoms changes the band gap energy values irregularly. Based on the obtained results, it can be concluded that the most reactive structures are that consisting of 3 aluminum atoms, 4 gallium atoms, and 2 indium atoms. Moreover, the substitution of Z hex C45 with 4 gallium atoms has the highest electronegativity due to the small value of the optical band.
Poster number 8, presented by Professor Osama Osman, titled Modeling Study of Aluminum, Gallium, and Indium, Substituted Graphene Quantum Dots. Graphene quantum dots are a cutting-edge material that has excellent electrical, thermal, and mechanical characteristics, as well as minimal toxicity and powerful photoluminescence. These unique properties give graphene quantum dots the ability to be used in different electrical, optical, and optoelectric applications. Graphene quantum dots with functionalization, substitution, and/or doping have lately become a significant stage in developing improved materials with the qualities necessary to fulfill application requirements. So, in this work, graphene quantum dots were substituted by 4 aluminum, gallium, and indium atoms in the shape of a zigzag triangle for density function theory calculations to study the change in electronic properties. The density function theory was used to calculate the total dipole moment, the high occupied molecular orbital and lowest unoccupied molecular orbital bandgap energy, and the molecular electrostatic potential. The basis sets employed in the model structure were 6 to 31 grams dP for aluminum, gallium, and indium, and B3LYP, 3 to 21 grams for aluminium. The substitution of aluminum, gallium, and indium atoms increased the total dipole moment of graphene quantum dots while decreasing the band gap, especially when 2 atoms were filled. The substitution of 2 aluminium atoms was the most significant in lowering the band gap, dropping it by 0.122 electron volt. Whenever the loading atoms were increased, the molecular electrostatic potential map indicated that the red color on the graphene quantum dot map had changed from being isolated on one triangle side to being spread over the graphene quantum dot surface. As a consequence, the reactivity and surface area of the graphene quantum dot surface increased according to the substitution of 4 aluminum, gallium, and indium atoms.
Hi everyone, I will talk about the most trendy advanced two-dimensional material nowadays and its ability for sensing of carcinogenic materials. Our title here is Ability of Trihalomethane Sensing Using Functionalized 2D Mixing, which had a formula of Ti multiplied by N plus 1, C multiplied by N, and T multiplied by N, which T can be fluoride ions, chloride ions, oxygen ions, and hydroxyl ions. The problem statement can be stated here when we mentioned the interaction of trihalomethane, the most common group of carcinogenic chlorination byproducts of water sanitation, with a pristine mixene monolayer, and the many types of terminal function groups that can be placed on the surface are subject of this study. The total dipole moment increased, stepping for all mixene in oxygen hydroxyl ions, mixene oxygen fluoride ions, mixene oxygen chloride ions, mixene hydroxyl fluoride ions, and the mixene fluoride chlorine ions, and the mixene hydroxyl chloride ions, respectively, along with increasing in band gap energy to be 0.734 and 0.940 and 1.120 and 0.835 and last finally 0.927 electron volt. The computed result lead to the conclusion that termination atom's nature and the number had a variable and growing effect on the primitive mixene total dipole value. Utilizing the density functional theory (DFT), the absorption energy of trihalomethanes on the surface of different mixene types were determined. The most reactive and stable chlorinated structure with a total dipole moment of 12.443 dpi and the band gap of 0.570 electron volt was produced through geometry optimization and computation. Since the mixene chloride layer may function as a sensor for most common types of trihalomethane species. Thanks.
I am Asma Muhammad Ismail. I am researcher in Spectroscopy Department, National Research Center. My poster entitled On the Molecular Spectroscopic Analysis of Ketosane Iron Oxide Nanocomposite. In this work, we discuss the effect of addition of iron oxide on ketosane to be used as a biosensor for amino acid glycine. As known, ketosane is an amino acid polysaccharide and it's biocompatible and has many applications in medical field. Also, iron oxide are the most famous and popular kind of magnetite nanomaterials and are used in many applications because of their low cost, low toxicity, and good magnetic properties. The magnetic nanomaterials are mainly prepared in the presence of two major aqueous solutions, which are ferrous and ferric as cleared in the preparation scheme. As observed, FTIR and XRD confirmed the complexation and interaction between ketosane and iron oxide, as also banded energy and absorption age changed on the addition of iron oxide on ketosane, which indicated the high density of the localized tail state in ketosane iron oxide nanocomposite. Also, UV visible spectroscopy resulted indicate that ketosane with 0.25 iron oxide ratio has sufficient sensitivity compared to pure ketosane and other ketosane iron oxide nanocomposite. Correlating the obtained data together, it can be concluded that ketosane iron oxide could act as a biosensor for the amino acid glycine.
عنوان البحث وهو تقييم الخصائص البصرية للأغشية الرقيقة ذات التركيب.
بسم الله الرحمن الرحيم. I am Isra Sulaiman Ahmad, master's student in the Department of Physics, Faculty of Women for Arts, Science and Education in Shams University. This poster is about energy storage, overview and outlooks. Aim of the research is studying the electronic properties of graphite, graphene and fluorine in order to investigate for energy storage application. The energy, environment and economy are the most fundamental global issues for our sustainable future. While energy is the most visual requirement for the progress of our civilization, where our current global energy consumption is about 15 terawatt, and we have become dependent on energy in various fields, where the statistic followed global energy consumption by sectors for the year 2021 is as 30% for transport sectors, 20% for industrial sectors, 13% for residual and chemical sectors, 36% for electrical power. So the statistic followed global energy consumption by different sectors as 33.6 for petroleum oil, 23.9% for natural gas, 27.2% for coal, 4.4% for nuclear energy, 6.8% for hydroelectricity, and for renewable energy 4%. That is almost 85% of energy is based on fossil fuels. It is expected that the global energy consumption increase with increasing technological and industrial development during the next 10 years. The only way to address this situation is to depend on renewable sources, but renewable sources are intermediate sources, and here came the concept of energy storage, as the energy storage provides resources, helps integrated renewables, provide financial benefits to minimize the dependence on fossil fuels. Hydrogen is regarded as the most promising energy carriers because its release is completely free from environmental hardness. And there is two ways for storage hydrogen are physical based and material based. Physical based is required requirements and technological that are costing, and the material based is the best ways to the storage hydrogen, like liquid organic, metal hydrates, and complex hydrates, and the carbon materials. And thank you for your attention.
Computational notes on the effect of lithium, sodium, and potassium on the vibrational spectra of fatty acid by شيماء جمال, فاطمة عادل, and محمد المنسي. Physics Department, Faculty of Women for Art, Science and Education, عين شمس University, Cairo, Egypt. Department of Physics, Faculty of Education, عين شمس University, Roxy, Cairo, Egypt. Fatty acid derivatives are the primary components of lipids, a model molecule of fatty acid which is composed of hydrocarbon chain terminating with carboxylic group. The model is subjected to molecular modeling calculation using the FT level of theory. Operational assignment of the model molecule is given in terms the calculated infrared and Raman are calculated at the same level of theory. For each band, the band position and its assignment is given. Besides vibrational characteristics, some important physical parameters are also indicated at the same level of theory. The parameters including HOMO-LOMO, band gap energy, and total dipole moment. Building a model molecule, the proposed structure of the studied fatty acid, neovidadin, consists of 20 atoms of carbon and 38 atoms of hydrogen attached to one carboxylic group. The activity of the neovidadin acid was improved by the substitution of hydrogen atom of the carboxyl group with different alkali metals such as lithium, sodium, and potassium. FTIR analysis. Figure 1 presents the IR spectra of neovidadin acid and neovidadin substituted with lithium, sodium, and potassium calculated at the FT. The C double bond O stretching vibration of the neovidadin's carboxyl group is found at 1839. C double bond O is shifted to the lower wave number region via interaction with lithium, sodium, and potassium cations. The OH scissoring for primary is found at 682, while OH wagging is at 554. Opens interaction with lithium, sodium, and potassium cations. H protons splitting takes place. The scissoring mode is shifted to the higher wave number region and observed at 753, 727, and 715 centimeters minus 1 for lithium oxygen, sodium oxygen, and potassium oxygen functional respectively. Also, wagging mode is shifted to 644, 618, and 603 centimeters minus 1 for lithium oxygen, sodium oxygen, and potassium oxygen functional respectively. Computational notes on the effect of lithium, sodium, and potassium on the vibrational spectra of fatty acid by شيماء جمال, فاطمة عادل, and محمد المنسي. Physics Department, Faculty of Women for Art, Science and Education, عين شمس University, Cairo, Egypt. Department of Physics, Faculty of Education, عين شمس University, Roxy, Cairo, Egypt. Fatty acid derivatives are the primary components of lipids, a model molecule of fatty acid which is composed of hydrocarbon chain terminating with carboxylic group. The model is subjected to molecular modeling calculation using the FT level of theory. Operational assignment of the model molecule is given in terms the calculated infrared and Raman are calculated at the same level of theory. For each band, the band position and its assignment is given. Besides vibrational characteristics, some important physical parameters are also indicated at the same level of theory. The parameters including HOMO-LOMO, band gap energy, and total dipole moment. Building a model molecule, the proposed structure of the studied fatty acid, neovidadin, consists of 20 atoms of carbon and 38 atoms of hydrogen attached to one carboxylic group. The activity of the neovidadin acid was improved by the substitution of hydrogen atom of the carboxyl group with different alkali metals such as lithium, sodium, and potassium. FTIR analysis. Figure 1 presents the IR spectra of neovidadin acid and neovidadin substituted with lithium, sodium, and potassium calculated at the FT. The C double bond O stretching vibration of the neovidadin's carboxyl group is found at 1839. C double bond O is shifted to the lower wave number region via interaction with lithium, sodium, and potassium cations. The OH scissoring for primary is found at 682, while OH wagging is at 554. Opens interaction with lithium, sodium, and potassium cations. H protons splitting takes place. The scissoring mode is shifted to the higher wave number region and observed at 753, 727, and 715 centimeters minus 1 for lithium oxygen, sodium oxygen, and potassium oxygen functional respectively. Also, wagging mode is shifted to 644, 618, and 603 centimeters minus 1 for lithium oxygen, sodium oxygen, and potassium oxygen functional respectively.
Bismillah ar-Rahman ar-Rahim. This article is development of mechanical and physical properties of material using a new irradiated ferrous alloy. The abstract, the purpose of this paper to study the physical properties of new alloy. The alloy contains mainly from steel. The change in constitute of alloy to development the mechanical properties of material to use in wide range of industrial applications. In this work, the effect of neutron radiation on hardness of material also is studied. This table 1, shows the contents of added elements of the main material. Is the conclusion of this paper. The hardness increases with the neutron irradiated. The atoms of this of the steel rearranged after neutron irradiation. The material which added enhances the mechanical properties. Thank you.
Glucose sensing utilizing biosensor based on graphene oxide, zinc oxide, polyvinylidene fluoride ADFD approach, presented by Manor Subhi. Hyperglycemia, high blood glucose, is poised to be one of the biggest healthcare situations in the coming decades, as major efforts are being put into new glucose monitoring systems. Accordingly, graphene oxide, zinc oxide, polyvinylidene fluoride model molecule-based biosensor was built up for glucose sensing. The proposed structures were optimized using the density functional theory at P3 and L to DZ level of theory. Total dipole moment, homolomo band gap energy, and molecular electrostatic potential were studied to demonstrate the findings. Firstly, building the model molecule of graphene oxide. After that, finding the total dipole moment and homolomo band gap energy with molecular electrostatic potential of graphene oxide. Then, the interaction of graphene oxide with zinc oxide occurred at terminal and middle on graphene oxide. The results show that the model molecule representing graphene oxide interacted with zinc oxide throughout the carboxyl group possesses the highest total dipole moment and lowest homolomo band gap energy. Additionally, the incorporation of the polyvinylidene fluoride to a graphene oxide zinc oxide molecule reduces the total dipole moment and homolomo band gap energy. Moreover, the molecular electrostatic potential shows that the interaction of the polyvinylidene fluoride with the graphene oxide zinc oxide model molecule increases the reactivity of graphene oxide zinc oxide molecule. Finally, the absorption of the glucose molecule to graphene oxide zinc oxide polyvinylidene fluoride model enhances the reactivity of the graphene oxide zinc oxide polyvinylidene fluoride molecule as total dipole moment increases and homolomo band gap energy increases slightly. This result shows that the graphene oxide zinc oxide polyvinylidene fluoride based biosensor is a good candidate for glucose sensing.
Welcome to our poster session. Poster number 23, electronic modification of PVDF hybrid membrane experimental and theoretical approach, presented by Amina Omar, lecturer of Biophysics, Faculty of Science and Shamsi University. In this work, we are focused in PVDF polymers. PVDF polymers is type of fluoropolymers, and which is the most common commercial and piezoelectric polymers that has promising use in smart biomedical and industrial membrane. Interaction of this zinc oxide and reduced graphene oxide polymer increase the beta phase of this polymer. Our work for making experimental and computational work. The experimental work focused in preparation of graphene oxide and reduced graphene oxide, zinc oxide, and forming hybrid membrane of PVDF with zinc oxide and reduced graphene oxide. And the computational work by using calculated of optimization and mapping electrostatic potential for this interaction through zinc oxide and graphene oxide. From the result of experimental work, the prepared PVDF hybrid membrane is characterized by XRD, FTIR, scanning, and EDAX. And we are forming from the experimentally that the senses of the PVDF zinc oxide membrane and the PVDF zinc oxide reduced graphene oxide membrane. And theoretically, from the DFT calculation, concluded that the PVDF interacted with the zinc oxide through the zinc, and their ability to interact with graphene, yielding a highly stable and highly reactive structure, which enhanced the potential for this hybrid membrane for using for virus biological application. Now the poster number 24 of polymethyl methacrylate PVDF hybrid membrane reinforced with 2D zinc oxide and graphene oxide theoretical and experimental approach, presented by Amina Omar, lecturer of Biophysics, Faculty of Science and Shamsi University. In this work also we focus on PVDF polymers, but we are reinforced it with the polymethyl methacrylate and forming composite between the polymethyl methacrylate and PVDF. Also, we have experimental and theoretical approach. The experimental work focus on the preparation of the graphene oxide with zinc oxide and the hybrid membrane and the composite membrane between polymethyl methacrylate and PVDF and graphene oxide and zinc oxide. And the computational work also making by density functional theory to have the mapping electrostatic potential and HOMO-LOMO orbital distribution. From the experimental result, we focus on XRD and FTIR and UV visible to have the band gap. And we are, from the result, we are ensure that the senses of polymethyl methacrylate PVDF graphene oxide and for hybrid membrane, and also for polymethyl methacrylate PVDF zinc oxide graphene oxide hybrid membrane. And from theoretical results, we have the total dipole moment and the band gap energy and the molecular electrostatic potential calculation reveals that the novel structure of the polymethyl methacrylate PVDF zinc oxide graphene oxide composite has the lowest band gap and the maximum total dipole moment, which enhances the potential for optoelectronics material.
Synergistic interaction between noble two-dimensional material reduced graphene oxide and biodegradable natural polymer sodium alginate was created by green and simple method to form unique microsphere with needle shape acting as super encapsulation and sustained release machine for highly effective and remarkable antibiotic cefotaxime. We developed three forms of microsphere: alginate cefotaxime, and alginate cefotaxime graphene composite were prepared using calcium chloride as a cross-linking agent and characterized using field emission scanning electron microscopy and Fourier transform infrared spectroscopy to investigate the pores, roughness, surface morphology, and to analyze the functional groups of the microspheres respectively. XR diffraction was employed for the identification of phase formation, purity, and structural properties. Membrane diffusion method was employed to determine release profile of cefotaxime from the fabricated microspheres. Antibacterial activities of cefotaxime solution, alginate microspheres, alginate cefotaxime microspheres, and alginate cefotaxime graphene oxide microspheres were investigated against gram-negative bacteria Escherichia coli using agar diffusion method on molar Hinton agar. The prepared samples gave excellent results.
Poster number 26 titled Electronic Properties and Molecular Electrostatic Potential Mapping of Graphene Quantum Dots Decorated with Zinc Oxide, Copper Oxide, and Titanium Dioxide, presented by Asma Ibrahim. Graphene quantum dots, hexagonal and triangle cuts with armature and zigzag ends, were decorated with different metal oxides such as zinc oxide, copper oxide, and titanium dioxide. The impact of metal oxide decoration on the electronic characteristics of graphene quantum dot was investigated using homolomo orbital distribution and molecular electrostatic potential mapping calculation. The model structure were calculated using density function theory. Calculation details: quantum dots in 4 different forms interacted with metal oxides such as zinc oxide, copper oxide, and titanium dioxide following the density function theory B3 lib LAN L2DZ model calculations. Models proceeds with Gaussian package at molecular spectroscopy and modeling unit, National Research Center, Egypt. The total dipole moment, homolomo the orbital distribution, and molecular electrostatic potential mapping were conducted for the studied model structures to investigate electronic properties of a chosen graphene quantum dots shapes interacted with zinc oxide, copper oxide, and titanium dioxide. Objective: tuning the electronic properties of graphene quantum dots by decoration with zinc oxide, copper oxide, and titanium dioxide. Conclusion: density function theory have been used to study electronic properties of graphene quantum dots and graphene quantum dots attached with metal oxide. The attachment of metal oxide significantly increased the total dipole moment with very high value observed in graphene quantum dots attached with zinc oxide. The increase in total dipole moment reflects the fact that the given structure are highly reactive with their surrounding media. The adding of metal oxide decreases the band gap energy. The most effective metal oxide of graphene quantum dots was titanium dioxide that enhanced band gap energy, and the theoretical IR of graphene quantum dots of various forms was computed and compared to ATR FTIR spectrum of produced graphene quantum dots. From the result, the characteristics band of theoretical IR spectra of several kinds of quantum dots are almost the same as in the experimental spectra.
Hello everyone, I'm glad to be with you today presenting our group's work, including myself, Salma Yunus, Ahmed Al-Sayed, Suhaila Salah, Dr. Amina Omar, and Dr. Medhat Ibrahim. Our work entitled Computational Notes of Catechol O-methyltransferase Inhibitors for Parkinson's Disease, a Treatment. Parkinson's disease affects the nervous system, which arises in several physical motions due to the depleted dopamine levels. Through dopamine pathway here, we can see vital enzymes such as RCUMT or catechol O-methyltransferase, which converts neurotransmitters such as dopamine into their methylated form. The medications rely on dopamine replacement, like levodopa. When levodopa enters the body, it's converted into its methylated form through a COMT enzyme, peripherally, thus decreasing the percentage of levodopa that enters the blood-brain barrier. When levodopa crosses the blood-brain barrier and generates dopamine, the COMT do his job one more time and convert the dopamine into its methylated form, thus decreasing a dopamine level. As we can see here, blocking COMT action can arise with increasing levodopa bioavailability as well as dopamine levels. There are 2 FDA-approved inhibitors for COMT, but they fall short to influence the fluctuations in the levodopa plasma profile, and one of them do not penetrate the blood-brain barrier. Here we are suggesting 5 new drugs through QSAR analysis that penetrate the blood-brain barrier. and comparing them with widely known inhibitor called 3,5-dinitrocatical or DNC. The suggested drugs have been chosen according to their pharmacophores. They are all catechals, so they can provide competitive inhibition of enzyme. Firstly, as you can see here, we draw the interactions between enzyme pocket and the drugs. Each drug is interacted through two hydrogen bonds between two residues, which are glutamate 199 and lysine 144. Also, there are two coordination bonds with magnesium ion. We did a QSAR analysis by calculating electronic descriptors like energy gap and hydrophobic descriptors like the partition coefficient, and also there are steric descriptors like molar refractivity. From the results, we can conclude that there are two promising drugs that penetrate blood-brain barrier, having more stable interaction with enzyme corresponding comparing to original drug, and have larger gap energy than DNC. Thus, they are less reactive toward the surrounding, and they can also fit into the bucket according to volume and surface calculations. Thank you.
Welcome to our poster session. Now the poster number 28 on the title Molecular Modeling Approach of Effect of Graphene Oxide, Titanium Oxide, and Silicon Oxide on Phospholipid Membrane is presented by Dr. Amina Omar, Lecturer of Biophysics, Faculty of Science, and Shamsi University. The membrane is an important component of a biological cell because it separates the content of the cell and organism from the surrounding fluid. The membrane composed of phospholipids, bilayers, and protein. The membrane phospholipids are one of the primary components of the cell membrane, which are selectively permeable and thus regulate the entry and exit of material or molecules in the cell. The phospholipid composed of hydrophilic head and hydrophobic tail. Changing the composition of the hydrophobic head and hydrophobic tail is changing the type of phospholipids membrane. There are two types of the membrane phospholipids, glycerophospholipids and sphingolipids. In this work, الفوسفوديالكولين POC and الphosphoethanolamine as a type of glycerophospholipids and sphingomyelin PSM as a type of sphingolipids. The molecular interaction of these phospholipids and its interaction with the nanomaterial as graphene oxide, titanium dioxide, and silicon oxide through oxygen of phosphate group of the phospholipids are calculated by using density functional theory. The calculated electronic properties and mapping electrostatic potential indicating the high reactivity of phosphocholine POPC and the phosphoethanolamine POPE interacted with the titanium oxide and sphingomyelin PSM interacted with silicon oxide. And from the result of the QSR parameter calculated at BM6, indicating increasing of lipophilicity for the phospholipids interacted with the titanium oxide and silicon oxide, which mean increasing absorption of this oxide on the surface of the membrane phospholipids to be used for different biotechnological and biomedical application.
Poster number 29, and its title is Functionalized Alumina Nanoporous Membrane for Neural Disease Treatment, presented by me, Nuran Ismat Said. One of the problematic issues in conventional treatment methods for the neural disease is their spread to other organs rather than the targeted nervous system, which causes toxic effects to the vital organs. So, in this work, we focused on using nanoporous alumina membranes as a drug carrier in order to overcome these problems. Nanoporous alumina membranes were prepared by a two-step electrochemical anodization method. The preparation process divided into 6 main steps. The first step is the pre-treatment step, in which the aluminum sheets were heated at oven at 500 degrees and then sonicated in sodium hydroxide and acetone. After that, the electropolishing step, in which the aluminium sheets were electrochemically polished in a mixture of perchloric acid and ethanol to reduce the surface roughness. After that, the aluminium sheets were first anodized in 0.3 molar oxalic acid at a potential of 40 volts for 5 hours. Second anodization was carried out similarly as in the first anodization, but for different time. Between the two steps of anodization, a selective remover of the porous oxide layer obtained by first anodization was done to pre-structure the aluminium surface. This etching process has to be done using a mixture of chromic acid and phosphoric acid at 70 degrees. The resulting inner surface of aluminium exhibits a uniform concave nanoarray based on which an ordered pore size distribution can be built. These nanoporous aluminum membranes were characterized by scanning electron microscopy, atomic force microscopy, and X-ray diffraction analysis. Density functional theory calculations were performed on aluminum membranes coated with different coating polymers as BVDF and BVB to test the biological activity of these coating materials on the surface of aluminum membrane. The results in table showed that structure number 8 was more stable and had lowest energy and highest reactivity. So this aluminum membrane can be used as a drug carrier for the treatment of neural disease.